So this video is on how ionic compounds dissolve in water and how you figure out whether the substance itself is actually going to be soluble or not. So the organizer that we are going off of is on page 430. There's a couple of terms on this organizer that you have not seen before because we're rearranging the order of how we're doing things in class this year. So you'll see one phrase here, IMFA, stands for intermolecular forces of attraction. We'll learn about what that is a little bit later, but at this point, don't worry about it. Just take the information as it comes. All right, so remember that we have this ionic crystal, and there are all sorts of electrostatic attractions holding that crystal together. All the cations are attracted to all of the anions in that complex alternating crystal. So in order to break it apart, there's three things that we have to do, and you can see those listed here. So first thing is, we have to break the attractions between the anions and the cations of the crystal. So to do that, you have to add energy. It requires energy to break any sort of attraction. So we have to add energy. The other thing we have to do is separate the water molecules. They have strong attractions to each other because they are very polar molecules. And so they have positive ends and negative ends as well, so they're very attracted to each other as well. We have to break those apart. But then, once we break those apart in step 3, we can create new attractions where the water molecules are attracted to the ions in the crystal. So what I want to do first is show you a video of how dissolving works. So I'm going to shift gears, go to a video from YouTube, and we're going to walk through how a ionic crystal dissolves in water. Okay, so there's the water molecule you can see. It's got the two hydrogens, the smaller parts at the top, and the oxygen, the bigger blue one. And then you have the salt crystal. You have the positive sodiums and the negative chlorines. And so like I said, water is polar because the hydrogens are, oxygen is more electronegative than hydrogen, so the electrons are pulled towards that. Sodium, you have the positive cation, which in this case is red, the negative anion. And so take a look what happens when water molecules come close to a salt crystal. The attraction for the positive hydrogen and the negative chloride is pretty strong, and vice versa, the attraction for the negative oxygen and the positive sodium is pretty strong. And so look what happens. You get this surrounding of each ion crystal by the water molecules, and that's going to continue to happen as you stir the solution to try and dissolve the crystal. Water molecules are going to constantly come into contact with the ions and start pulling them apart, and this is happening because the lattice energy of the crystal is weaker than the attractive forces of the water and the salt. So you have a case where that substance is considered soluble. So if a substance is soluble, the formation of those ion dipole attractions, the cations and the anions to the dipoles in the water molecule, that attraction is going to be very strong, and so the substance will dissolve. And remember I said that the cations are going to be attracted to the negative oxygen, the anions are going to be attracted to the positive hydrogen. And so what you're going to see is visually, you're going to see the cation surrounded by the oxygen part of water. Okay, and then the anion will be surrounded by the hydrogen part because oxygen is more electronegative, so oxygen will have that negative, that partial negative, right? Partial negative. Hydrogen will have that partial positive. So the positive parts of hydrogen will be attracted to the negative anion. Again, electrostatic attractions. The negative part of the water molecule will be attracted to the positive cations. And so we call this an ion dipole interaction. Okay, so if the substance is soluble, these attractions are much stronger than the lattice energy. However, if the ionic substance is insoluble, so we've seen that a couple times, you saw magnesium oxide didn't dissolve in water even though it's soluble, because the attractions for the ions to each other are stronger than the attractions of the ions to the water. So what's going to happen? You're going to see nothing change. The crystal will just sit on the bottom of the beaker. Here, as the salt dissolved, you see the solution pretty much go clear because all of the ions have dissipated into the water. Now, when we talked about strength of attraction, we were talking about how the lattice energy is a little bit different. So what I want to do, in order to show that, we've got something called solubility rules. So what we're going to do is we're going to take a look at a set of solubility rules. I probably should pull this back up a little bit so you can see the whole set. So solubility rules, you have these in your appendices. They are a set of rules that let us predict whether or not a substance is going to dissolve. So if you look, most of these rules are based on the anion. So we're going to start with the anion, and then we'll look to see what cation it's associated with. And if you look more closely, okay, so for example, the chloride rule and bromide and iodide, so the halogen rule, most metal chlorides, bromides, and iodides are soluble with a few exceptions, except those of silver and lead. Lead 2 chloride is moderately soluble. So what we're looking at here is you have something like potassium chloride, it's going to dissolve in water. You have something like calcium chloride, it's going to dissolve in water. The only things that aren't going to dissolve in water are chlorides, bromides, and iodides with these cations, silver and lead. So that's how you use the solubility rules. There's a couple other things to note here. So for example, here look at carbonates. It says carbonates are insoluble except those covered by Rule 1. Well, okay, let's go up and look at Rule 1. Rule 1 says alkali metals and ammonium salts are soluble. So anytime I have potassium, sodium, lithium, no matter what that is, all of those salts are going to be soluble. Likewise, ammonium. So ammonium phosphate, ammonium chloride, ammonium whatever, those are all going to be soluble. So Rule 1 is the only rule that focuses on the cation. Everything else you will see focuses on the anion. So let's use these rules to predict. And these rules apply the idea of lattice energy. So for example, the alkali metal rule, those are all +1s, right? So they have less attraction than something like chromate, which is -2. Hydroxides, well, -1. Oxides, -2, and so forth. So they take the ideas of size and charge, what we learned about lattice energy, and put them down into kind of an organized fashion. So let's use these solubility rules to predict whether or not you're going to see a precipitate. So, or whether or not it's going to dissolve, first and foremost. So you take a look at substances like this. So barium nitrate. So what do I want to do? I want to focus on the rule that says all nitrates are soluble, the nitrate rule. Well, okay, so then that's easy. All nitrates are soluble. So then barium chloride will dissolve. Yes, it's going to be soluble. Okay, what about potassium phosphate? So what am I going to do? I'm going to go to the phosphate rule. Okay, so there's the phosphate rule. Phosphate rule says all phosphates are insoluble except those covered by Rule 1. Now remember, Rule 1 was alkali metals are always soluble. Potassium is an alkali metal, so yep, that's going to dissolve in water. If I go to calcium carbonate, okay, carbonates are insoluble except those covered by Rule 1. All are soluble in the presence of acid. So we're not dealing with acid, we're just dealing with water. So calcium carbonate is insoluble because calcium is not Rule 1. It's not an alkali metal, it's an alkaline earth metal. So in this case, calcium carbonate would be insoluble. So no, it's not going to dissolve when I put it in water. Okay, so there's 3 more take your time, use your solubility rules. Again, those are in your appendices, so I apologize for not telling you in advance to pull them out. Pause the video, pull those rules out if you don't have them, and then try your hand at these last three, and then we'll see what you come up with. Okay, so you've paused, and I'm assuming that you've used your rules, so let's see. Silver chloride, so let's go to the chloride rule. Most metal chlorides are soluble except those of silver. So this one is going to be a no. That one's going to be insoluble. Okay, aluminum sulfate. So find the sulfate rule. Sulfates are soluble except those of barium, strontium, lead, calcium, and silver are moderately soluble. So aluminum is none of those. So aluminum sulfate is going to dissolve. And then finally, iron chromate. Chromates are insoluble, except those covered by Rule 1 and those of magnesium, manganese 2, and iron 2. So chromates are insoluble, except those covered by Rule 1, manganese 2, iron 3. Doesn't say anything about iron 2, and if we go back and look at our formula, this is actually iron 2 chromate. Chromate is -2, so to have a 1-to-1 ratio, it must be iron 2. So this guy is going to be soluble. He's going to dissolve in water. If it were iron 3, we would say no. Okay, so that's how solubility works. That's how the solubility rules work. Our next plan is to use solubility rules to take a look at what happens when we combine ionic compounds, but we're going to do that in the next video.